The next presentation title will be a probability assessment of tempered glass failure based on high fidelity process and in service modeling techniques. And the speaker is Mondragon, sorry, not the speaker, Asier Sanchez. And Asier is working at the moment as a lecturer and researcher in the Thermofluids department of Mondragon University, and just presented his PhD thesis entitled Methodology for Assessing the In-Service Behavior of Glass Plates Considering the Effect of Residual Stresses. Very good, Asier, the floor is yours.
Okay, thank you, Mika, for the kind introduction. So my name is Asier Iglesias. I'm coming from the University of Mondragon, and I will talk about the work that we have done in collaboration with the University of Oviedo, which is entitled Probabilistic Assessment of Tempered Glass Failure based on high fidelity process and in-service modeling techniques. So I have divided this presentation into 5 main sections. Firstly, an introduction, followed by a fluid structure interaction methodology to predict residual stresses. Then the probabilistic assessment of tempered glass failure, some conclusions, and finally, some future work. So, have you ever wondered how many glass applications do we see in our daily lives where glass is used as a structural material? Being here, I'm sure that you have. So, we can encounter structural glass in buildings, vehicles, solar panels, and home appliances. Recently, with the aim of achieving lightness and transparency, large surface components are sought. This can be seen in building facades or in vehicles where the sunroofs have evolved from being small openings to cover the entire roofs of the cars. Similarly, the glass industry is trying to reduce the weight of its components to decrease the cost of the raw material, energy, and transportation. Not only the glass industry, but also during in-service operations, to decrease the weight of the components means to decrease the energy consumption, for example, in electric vehicles, or to select smaller frames to support those glass panes in the architectural sector. So this weight reduction is obtained by reducing the thickness of the components. However, thinner material also implies the obtention of a weaker component. So because of this reason, glass is most often heat-treated or tempered to strengthen the material. So apart from the tempering process, we have to bear in mind the surface defects of glass. These surface defects are developed unintentionally during the manufacturing or usage of glass, and both aspects need to be considered when assessing the in-service behavior of structural components of glass. So the tempering process consists of cooling glass by air jets from a temperature above the glass transition temperature, which is around 650 degrees. And the aim is to obtain surface compressive stresses to strengthen the material. So if we look at the residual stress distribution through the thickness of the glass pane, we would have surface compressive stresses, and inner tensile stresses. Focusing on the industrial tempering process, we would have a glass plate, some rollers, and air cooling jets. These air cooling jets lead to non-uniform heat extraction on the surface of glass, and as a result, we will have a non-uniform heat transfer coefficient on these surfaces. These have a direct impact on the subsequent non-uniform residual stresses that are developed during the tempering process. During modeling, to consider a constant and uniform heat transfer coefficient may impede the obtention of that non-uniform residual stresses during the calculations. Such as in here, as we can see by a polariscope, these non-uniform residual stresses, or here in a 3D measurement surface, also we can see these non-uniformities. So these aspects have a direct impact on the structural and aesthetic features, and we can see this in the anisotropy that we can see in tempered glass panes, such as in building facades or in the rear windows of cars. Additionally, we have to take into account the surface defects. So if the size of these defects is lower than the compressive layer of our glass pane, no failure occurs. But if this surface flaw is larger, catastrophic failure is bound to happen. In addition, we have to bear in mind that the failure characterization of glass components requires a huge experimental effort. So the objective of this research is to develop a numerical methodology to predict the in-service behavior of glass plates subjected to bending loads, considering the residual stresses that are developed during the cooling down process. So the idea is, could it be possible to characterize the failure of annealed glass plates and use that data to predict the in-service behavior of tempered glass plates, tempered conventionally, symmetrically, or glass panes showing any other residual stress distribution? So we will see that in the following slides. So firstly, we propose a fluid structure interaction methodology to predict the residual stresses. Why? Because the tempering process is a multiphysics problem where we have different fields interacting with each other, the thermal, mechanical, and fluidic fields. So a fluid structure interaction methodology allows us to couple all these fields working together with the aim of capturing that non-uniform temperature distribution over the glass surface and the non-uniform residual stress distribution. In this context, what we propose is a computational fluid dynamic analysis to obtain the non-uniform and transient temperature distribution in glass, and we transfer it to a mechanical model where we consider the viscoelasticity and structural relaxation phenomena of glass. In this way, we are able to predict the non-uniform and transient residual stresses. For validation purposes, we propose a single jet case study that was carried out in the facilities of the University of Mondragon. And with the aim of analyzing the in-service behavior of different plates exhibiting different residual stresses, we propose the following case studies, where we have annealed glass as a stress-free glass component, asymmetrically tempered glass resembling the conventional heat treating, and an asymmetrically tempered glass which was selected as a string case where most of the heat is extracted only from one side of the plate. Similarly, we analyze different jet-to-plate distances to analyze different residual stress magnitudes. As a result, we would have 150 samples to be tested. So first, we performed the tempering test on the facilities of the University of Mondragon. Here you can see the frame that was used to support the glass samples vertically. The side length of these samples was 90 millimeters. And we can have a look at the recordings of the thermographic camera, where we can see that a shorter jet-to-plate distance leads to higher cooling rates and thus a faster cooling. After doing the tempering test, we took residual stress measurements by a scattered light polariscope and a CNC coordinate machine. And after performing those experimental tests, we developed a numerical model to represent this test. So it was first a computational fluid dynamic model, where we would have the air domain, the plate, and the nozzle. And here you can see the mesh, where we obtain the temperature distribution, and we transfer it to a structural model composed of the plate, of the glass plate, to calculate those residual stresses. So turning now to the validation of the results. Here we can see the residual stress distributions for the symmetrical tempering case. From left to right, we can see the experimental values, the numerical predictions and the difference between them. And on top, you can see the short jet-to-plate distance, and below, the large jet-to-plate distance. So here we can see that predictions were more accurate on the stagnation areas of the jet, mainly in the center of the plate. And here we can see the residual stress distributions along the X and Y directions of the plate. The experimental measurement band was composed of the repeatability test and the uncertainty range of the scalp device. Following a similar procedure, we can see the residual stress results for the asymmetrical tempering case. So from left to right, you have the experimental, numerical, and the difference between them. And on top, the short jet-to-plate distance, and below, the larger jet-to-plate distance. And likewise, we can see the residual stress distributions along the X and Y directions. So after validating the residual stress prediction, we turn to assess the in-service behavior of these components. And to this end, we make use of the generalized local model, which was proposed by Miguel Muñiz Calvente from the University of Oviedo. So first of all, we carried out the experimental program of coaxial double rings to determine the bending strength of these plates. Then we calculated the distribution of the generalized parameter. This parameter is related to the selected failure criterion. And in this work, we analyzed two failure criteria, the maximum principal stress criterion and the principle of independent action. Afterwards, we developed an experimental failure cumulative damage function to begin with an iterative process to determine the weighable parameters, the shape, location, and scale factors, to determine the primary failure cumulative damage function, which is a function which behaves as a material property, and it's independent from the experiments done or the samples that are used. So as a result, we will have, for each glass type and each failure criterion, some weighable parameters, and we propose the following analysis. To predict the in-service behavior of annealed glass plates, taking into account the parameters of the tempered glass, and to predict the behavior of tempered glass plate, considering the parameters of annealed glass, to see if this transferability is possible. So first, if we analyze the failure of annealed glass, here we can see the circles that are the experimental strength values for annealed glass plates, the ones that we have tested. The continuous black and gray lines refer to the predictions of our model. The colors refer to the selected failure criterion. And the dashed lines refer to the 5% and 95% confidence interval. So now, if we take the parameters of the tempered glass characterization, we could predict the annealed glass behavior making use of the parameters of the tempered glass characterization. So overall, we identified that the average error was of 10%. And we can do a similar procedure for the tempered glass failure, taking into account just the parameters obtained from the annealed glass characterization. We could predict the in-service behavior of the tempered glass, the different cases that were studied in this work, based on the parameters of annealed glass. So we confirm the transferability of the results, even if different residual stress patterns were considered. So now I would like to draw the main conclusions. So to remember, the main objective was to develop a numerical methodology to predict the in-service behavior of glass plates subjected to bending loads, considering the residual stresses developed during the glass cooling down process. And in this context, we propose a numerical probabilistic methodology to assess the failure probability of tempered glass based on the experimental characterization of annealed glass plates. Here, we will have a fluid structure interaction methodology to account for the non-uniform cooling and calculate the representative residual stress distributions. And by the generalized local model, we verify the transferability of the results between the plates exhibiting different residual stresses. So this methodology can contribute to reduce the total experimental effort as well as the economic cost involved in the fracture characterization of glass components. A more in-depth analysis of this work can be found in the following paper, which was published last year in collaboration with the University of Oviedo. And a natural progression of this work would be to extend this analysis to a real structural glass component, namely an industrial case study where multiple jets are used. And in this sense, we have taken the first step, as we have published also another paper last year where we use the proposed fluid structure interaction methodology. And in this case, the case study was based on an experimental case study from the literature where multiple jets were shown. We validated our results with the experimental data available there, which was a tempering case, and the side length of those plates was 300 millimeters without oscillation, were no rollers in that experimental case. It was the data available in the literature. And similarly, we did a sensitivity analysis of the initial tempering temperature to see its influence, and the experimental data, or our predictions, came into agreement with the experimental data shown in this publication. So in this way, we could validate the fluid structure interaction methodology even when multiple jets were used. So overall, the proposed numerical methodology can minimize the iterations needed when designing, manufacturing, testing of prototypes, resulting in a significant reduction of the economic cost and cycle time involved. So, kiitos paljon.